We're going to look here at a calculation or a set of calculations to do with buffers. So the first thing I'm going to address is what is a buffer? Well, a buffer is a solution that's made up from a weak acid and its conjugate base, or a weak base and its conjugate acid. However, my suggestion is to remember it as the former of those. A weak acid, in this case it's that chloride salt there, and its conjugate base. Because by remembering that definition, you can remember the first step to do when you've got calculations, and that is to write an equation for the dissociation of that acid in water. So we're going to do that here. Now you'll notice that I'm going to remove the chloride ion. That's because chloride ions are spectators when it comes to acid-base reactions. So chloride being -1 means that CH3NH3 must be +1 for charge. Dissociation with water, because these are aqueous solutions, so water must be present, and I know that weak acids and weak bases react with water. You'll notice I'm given a pKa. That's my other hint that maybe in this I should be looking at the acid dissociating rather than the base. If I was given a pKb, yep, maybe I'd look at the base dissociating with water to make the acid and hydroxides. But in this one, whoops, got a mistake there, sorry. I am showing it acting as an acid. Now, it says in the question that both of the things I start with are in quite high concentration, so that's good. That means that this is going to be probably a very effective buffer because they're starting at 1 mole per litre. However, because they're both solutions and they aren't the same volume being added, these concentrations are going to change. They're going to change, and they're also going to change relative to each other. So this one started off as 20 mils, and this one started off as 30 mils. Well, 20 plus 30 is 50, so I can do a ratio to find out what their new concentrations are going to be. So what I'm going to do is I'm going to go 1 for the moles per litre times 20 divided by 50 to find the new concentration. Now, you're not going to always start with 1 mole per litre. You'll often get ones that are a bit more complicated than that. So I'm also going to be careful by doing it on my calculator and not make any silly mistakes. So I just go 1 times 20 divided by 50 equals, and I get 0.4 moles per litre. So in this new solution, the concentration of the acid is only 0.4 moles per litre. And in the new solution, 1 times 30 divided by 50, so for this one here, ends up being 0.6 moles per litre. Okay, so we've got their new concentrations. That's really convenient because that means we know the concentration of this, and we're only trying to find our hydronium ion concentration. Well, that's good because the question is asking about pH, so that should be our unknown. Okay, so what links all of these things together? Well, if we've got an equilibrium equation, then we can write an equilibrium expression. And because it's making hydroniums, it's a Ka expression. So we've got the concentration of CH3NH2 times the concentration of hydronium over the concentration of CH3NH3 positive. Now I know these values, so that's nice and convenient. What about the Ka? Well, in the question I was given pKa, so I can take that value and I can use that to rewrite this equation as well. So I've got 10 to the power of -10.64. I know that's not good maths, but for me I like that. It's nice and easy for me to put into my calculator. Equals 0.6, this top value here, times hydronium ion concentration over 0.4, our acid's new concentration. Then what I can do is I can rearrange this to make hydronium my subject, because of course I want this to be the subject to find the pH. So I'm going to multiply both sides by 0.4, so 10 to the negative 10.64, whoops, times 0.4, and then I'm going to divide both sides by 0.6, and I'm going to solve. And when I put this in my calculator, so sorry, bear with me while I do this, 10 to the power of negative 10.64 times 0.4 divided by 0.6 equals, I get 1.5272, and it keeps going, so I get 1.53 times 10 to the negative 11 moles per litre. Okay, so now I've got that value, I need to remember how to turn that into pH. So I need to remember this equation. pH is negative log of the hydronium ion concentration. So I'm going to put this number here into that equation and work it out. Now I've still got the original value on my calculator, so I'm actually going to use the exact value, not rounding off. Either way, you're going to get the same answer, to be honest. So it doesn't matter which way you do it. If you do take it off your calculator, don't worry. So here we go. Negative log of my answer equals 10.816 something. Okay, so I get 10.8. And that's all that's required for that, because that's what the question was asking. What is the pH, or calculate the pH of the resultant buffer. Okay, so what are the key things I could do to just quickly check that I haven't made a silly mistake? Well, the first thing to notice is that pKa was 10.64, and the concentration and volumes of the acid and the conjugate base were very, very similar. The difference between 0.4 moles per litre and 0.6 moles per litre is not huge, not really. So we'd expect the pH to be very, very close to the pKa. And sure enough, 10.8 is very, very close to 10.64. Sorry. So it's very, very close to that. So that's my first check. Okay, I think I've got it right. The other thing that's a good check to do is what had more added. Was there more base, so more of this added, or more acid added, this one here? And what I look at is 20 mils versus 30 mils. There was more base added. So I expect my pH to be greater than my pKa. And sure enough, 10.8 is greater than 10.64. So that also reassures me that I've got it right. This is going to stop me going through each and every little step of my equation, of my working, to make sure I haven't made a silly mistake. In an exam, that's too tricky to do. So it allows me to go on with confidence, thinking, yep, I'm sure I've got my 10.8 correct. The other thing, just very quickly, I will comment, is I've put 10.8, not 11, for example. Even though in my working I've been very lazy with my significant figures, in the question, my volumes were given to 3 significant figures, and my pKa was given to 4. So I know that I can be precise to 3 significant figures at the end. This is part of a bigger question where those 1 mole per litre solutions were known to be correct to 3 significant figures as well. They were 1.00. It was a bit lazy of this examiner not to make it 1.00 moles per litre in these questions as well. But I mean, that's getting pedantic. So as I say, I'm going to quickly go through it again with you, but I can be very, very confident that 10.8 is correct. First thing, this is a buffer solution because I have an acid, a weak acid, and its conjugate base. They are in significant concentrations, and very similar concentrations, but they're both present. That means this can act as a buffer. So what I do next is this step here, where I write the dissociation of the acid with water. And that will show me the acid and the conjugate base both present in the equation. I then worked out their resultant concentrations, which is this line here, and plugged that into a Ka expression, which is this step here. Then I was able to solve for hydronium. Then I could use my hydronium ion concentration to find my pH, which answered the question. I knew that my pH was correct, or could be confident that it was correct, because it is similar to the pKa, and because more base than acid was used to make the buffer, it should be above the pKa. I'm now ready to move on to the next question with confidence that I've got this correct.